So in a previous video, we had a discussion about Markovnikov, right? And Markovnikov, we said, gives us an idea of how to label or predict the major product and the minor products that could form in a reaction. And we said that Markovnikov generally is used for unsymmetrical alkenes or alkynes. So I need a double bond or a triple bond, right? Okay, so in this lab, what you're going to do is that you're going to take one hexene. So let's draw the structure. The prefix hex in organic chemistry means 6. That's probably pretty important. You probably need to start memorizing these prefixes because if you don't need them for our class, you'll definitely need them for organic when you get to that point. But hexene means 6. So that means 6 carbons. 1, 2, 3, 4, 5, and 6. Now the ENE ending means double bond. I have a double bond in place. Now that double bond can happen anywhere. So I'm going to scratch my head and I'm going to say, well, where does that double bond happen? Well, the name should be very clear-cut decision of where that double bond is present, and that is a 1, right? So that's the purpose of writing the 1 out in front. It's letting you know that this double bond is happening on the very first carbon in that structure that you've drawn. So I need to put my double bond right there at carbon number 1. Now, again, I told you, this is not meant to be rocket science. I should be able to look at a name and just put the puzzle pieces together and kind of figure out what needs to go where. And this is the structure of 1-hexene. This is your starting reagent in the laboratory. This is where you're going to kind of start. And you're going to put this hexene into a boiling flask and a reaction is going to happen. Now, a little bit about hexene, or 1-hexene at least. I can give you some stats and a little bit of background about it. Number 1, it's very commonly used to make plastics. So in the plastic industry, maybe the plastic water bottles that you drink out of with your water or your milk, or any type of suitable container, it typically begins or involves at some point in time the molecule of hexene. So both plastics here are targeted. Your HDPE plastic and your LDPE plastic. That stands for high density and low density polyethylene. So the P stands for poly and the E stands for ethylene. So here is this other ENE ending. So start looking at these names and start putting these puzzle pieces together. So 1-hexene is an organic. It's all carbon and hydrogen mainly. That's what it is. So this is an organic molecule. It is very nonpolar, meaning it's not going to mix with water very well. It's very insoluble in water, actually. The boiling point of 1-hexene is going to be 64 degrees Celsius, give or take a little bit. So you're not going to have to heat it up to boiling point of water before the thing evaporates off. And this is traditional of an organic chemical as well. The density here is 0.678 on average gram per milliliter. This is less than the density of water, which again is very traditional when it comes to an organic molecule. And the formula weight for 1-hexene, you can look this up in Wikipedia or the Merck, but that's 84.16 gram per mole. So all carbon, all hydrogen across the board. So there's a little bit of background about 1-hexene. The next reaction that we're going to talk about, or not the next reaction, but the next reagent that we're going to talk about is sodium borohydride. This is the other component that you're going to add to the hexene in order to get it to do something. So sodium borohydride, what can we say about that? Well, sodium is Na, right? We know that. Borohydride. Boro is for boron. I can kind of see that name, that element name in the actual chemical name. And hydride is basically hydrogens. So sodium borohydride looks kind of like this. They like to put this in brackets to let you know that this stays together. And this sodium is kind of a positive piece, and this borohydride is kind of a negative piece. And these two things hang out together because there is an ionic bond in play. The Na plus and the BH4 negative. Kind of like sodium chloride, NaCl, right? Okay, so there's sodium borohydride. That's going to be used as a reagent. And because these things have charges, they're okay to be used in what we would call a protic solvent. So this is something that's polar in a way because I see some charge relationship here. And these things can dissolve in polar solvents because of that. They are very soluble in water. Sodium borohydride is soluble in alcohol. It's soluble really with anything that has a certain polarity that's associated with it. Sodium borohydride is called a reducing agent. Now, reducing agents mean something different in organic and in general chemistry. At least in the beginning, it seems like they mean something different. And they actually don't. It's just the way that they describe how these things work. So the way that I want you to think about reducing agents is I want you to think of it in this case as an agent that can reduce the number of carbon-to-carbon bonds. All right? So it promotes reduction in another compound. Reduction is the gain of electrons. So if you gain an electrons, a reducing agent allows oxidation to kind of take place. So all of these terms get intermingled in the courses, and I don't want you to get confused. So that's why I'm telling you, think of it this way. A reducing agent reduces the number of bonds between the carbons. In this case, this works out. All right? Sodium borohydride, where is it used? Well, very often it is used in the wood pulp industry. The reason they use it in the wood pulp industry is because it is used to dye and bleach the product. So we have kind of a wood pulp industry in town. It's right across the bridge. You can find it in Regalwood, and that's basically what they do. So this wood pulp is basically processed, and we need to bleach it and make it white so that something like notebook paper can come to you white and not brown or khaki in color. Sodium borohydride is also used in the pharmaceutical industry. Very common, it's going to be in there. And pharmaceutical industry typically uses it to make antibiotics. So this is a reagent that they will use in their formulation process. That is not uncommon. And this will end up with various types of different antibiotics that's out there in the field for the consumers to take. So two structures here. One hexene and sodium borohydride. But that's not the only two. Remember, I told you that this reaction you probably need to wait off on until you complete other labs before you get to this one. And that's because there's a lot of things that are going on. All right, so with that said, we need to talk about our next reagent. So 1-hexene, sodium borohydride, and the next one is going to be iodine. So iodine from the periodic chart, of course, is the I element. But this iodine is going to be in a solvent, and that solvent is THF. So what does this abbreviation mean? THF means tetrahydrofuran. And tetrahydrofuran is also another common solvent that you might see in a laboratory environment. I like to call this the cupcake molecule. And the reason I call it the cupcake molecule is because when you draw it, it is a 5-membered ring. And that 5-membered ring is not all carbon. One of these is actually an oxygen that sits up here at the very top. That's the little cherry on the cupcake. And then if I do that number, that looks like cupcake that has icing on it now. So I call this the cupcake molecule for that reason. But it's basically a 5-membered ring with oxygen in place of one of the carbons. So tetrahydrofuran, it does have a little bit of polarity. And the reason that it does is because this oxygen has got some free pairs of electrons that are associated with it. So it is polar, but it's also nonpolar. It's organic, but it's also non-organic. And THF is very commonly used to make polyvinyl chloride, or PVC. It's also a carrier solvent that's used in many varnishes that you might get at Lowe's or Home Depot. If you're redoing furniture or whatever the case is with woodworking, you can kind of see it there as well. And it can form clathrates at very low temperatures with water. So if you've not done the clathrate lab, you will end up knowing what a clathrate is. If you have done a clathrate lab and you forgot what it was, maybe go back and jog your memory, because THF can form clathrates with water under very low temperatures. All right? The LD50 for tetrahydrofuran. LD50 means lethal dose that will kill 50% of the population. It's very similar to acetone. So this is going to take quite a bit in order to kill you. But it is a possible carcinogen. So I don't want to be putting my hands in it. I don't want to be bathing in it. I don't want to be rubbing it on my skin. I don't want to be breathing a lot of it in, even though the LD50 is very, very high and the exposure limit is enormous for this molecule. It is associated with cancer. So I want to limit my exposure whenever possible. It does dissolve latex gloves, so you cannot wear latex when you work with THF. It will just eat right through those gloves and it will go right onto your skin. So you're going to have to choose something different than latex, and this is one of the reasons that we do not have latex that are lying around for the most part, because chemicals like this can react with them. It can eat the latex, so why even bother purchasing them? So we get the chemical resistant gloves instead. So that's a little bit about THF. So what happens here is that I'm going to take some iodine, and the iodine is going to be in a crystal form, or you will take iodine. That will be in a crystal form, and you will put that into a solvent, and that solvent will be THF. So this will turn in to be like a brownish liquid. If you've made it the right way, it's going to be darker in color, yellowy brown, maybe dark brown, but that's what your THF solution will look like. So the iodine crystal, non-toxic, it's a shiny crystal, very commonly used in the medical field, not a big issue there at all. It's just the THF that you want to be careful with when you handle it in the lab. All right, so as far as the reaction setup goes, those are my reagents. So how does this setup look? Well, the book is going to kind of walk you through what this thing needs to look like. So let me explain it just for a few minutes. So here at the bottom is going to be a bowling flask. And that bowling flask is going to have an adapter on it. And it's called a U adapter. The reason they call it a U adapter is because it makes a U. Go figure, right? So there's kind of the first part of the U, and that's going to go down into that bowling flask. And then up here at the top, that's going to be kind of the other part of the U. And the reason that we do this is because we want to slowly add iodine to the sample, but we do not want the iodine to basically, or we don't want to disconnect the apparatus to add the iodine throughout the reaction. So that's why we use the U clamp or the U adapter. So on one of these, well, it's going to be the reflux, okay? So I'm going to have a reflux that's going to be attached to one side of the U, and there's going to be a water in and a water out. And this is my reflux or my condenser. On the other side, I'm probably going to have something like a separatory funnel. We have some separatory funnels that are jointed with a 2440 joint. And these separatory funnels are pretty good because it allows me to add solution very slowly, drip by drip by drip, into the boiling flask that sits down below. So this separatory funnel is going to house my iodine with my THF. Okay? The boiling flask that sits down here at the bottom, that's where my hexene and my sodium borohydride is going to be present. I'm going to heat this reaction vessel up. And over time, I'm going to open the stopcock, and I'm going to allow the iodine in THF to slowly be added into that reaction flask, little bit by little bit by little bit. All right? Now, I said I'm going to heat the boiling flask up. The issue here, though, is that I think they give you a limit. And I think they say make sure that this stays below 50. So when I say heat it up, you're probably not going to have to put a lot of heat on this thing in order for it to work. And most people actually don't. They just allow the two things to mix, and they allow the two things to react together, and they monitor the temperature as that begins to go forward. If at any point in time that temperature goes above 50, we have a problem. So a cold bath is going to be very important. I want to make sure that I have a beaker full of ice water. And if this reaction gets too vigorous, and if the reaction generates too much heat, I want to be able to take that flask and put it into the cold bath as quick as possible so I can calm that reaction down. Throughout this process, the THF I told you was brownish, right? And that's due to the iodine. Well, the solution in here is going to be brown. And as it drips down into this flask, it's going to turn this flask down here in the bottom brown. But as the reaction goes forward, the brown color will slowly change, and it will go a very pale yellow to a clear color. You can see through it. It's not difficult. When that happens, that means the iodine's getting used up. And if the iodine's getting used up, that means the reaction's going forward like it should. It gives you a visual indication that this reaction is going forward like it should be. So, throughout the process, it's going to tell you, add some iodine. Let it go brown. Let it react until it goes clear or a very pale yellow. When it does that, add more iodine. And keep doing it over and over and over, and being patient and allowing this thing to react until you've added all the iodine that you're supposed to add. So in the next video, we'll continue on with the discussion of this lab, and we'll make our way finally to a reaction and to the mechanism of how this thing works.